welcome dear students and welcome back to the Learn Daily Physics. So today we are going to talk about Bose Einstein condensation, and we will see that what is this Bose Einstein condensation. So let's have an introduction first, that we have seen that what plasma is. Plasma is a fourth state of matter, we say, and it is formed by the ionization of gas at high temperature. So just like that, contrast to the plasma, we can say that we have another form of matter. It's not that well known form of matter, but it's still another form of matter which is called Bose Einstein Condensate. Okay, the form is called Bose Einstein Condensate, and today what we are going to talk about Bose Einstein Condensate, what it is and how it's formed. So let's have a look on our animation first, that what is a Bose Einstein condensation. Okay, now let's see that. You can see on your screen that we have some energy levels here. Here we have energy levels. This thermometer here is showing temperature. We have temperature here, and these are the motion of molecule, randomness of molecule. They have a kinetic energy. They are moving randomly everywhere. Okay, so let's see. They have high kinetic energy at high temperature. The bosons are, let's say these are the bosons, and these are the energy states. Okay, so at high temperature the bosons are at high energy levels. Some one is at ground state, two are at 3, 4, and like these, they all are at excited state 1, 2, 3, 4, 5 respectively. You can see as we decrease the temperature, let's see what happens when we decrease the temperature. So this is the temperature. We are going to decrease the temperature. You can see that bosons are jumping down. Okay, you can see on your screen that particles are jumping down toward the lower state. Okay, and their motion, now they're freezing out. Okay, their randomness is decreasing. Their entropies, we can say that their entropy is decreasing. Okay, so these particles are coming down at absolute zero. We can say near to the absolute, they form a single collective quantum wave called a Bose Einstein condensate. Okay, so what is Bose Einstein condensation and what is Bose Einstein condensate? This is now their collective wave. Let's get back. They have different energies, they have some different randomness in them, they have different motion, their energy levels are different, their wave function will be different. But when we decrease the temperature below their degeneracy temperature, what is degeneracy temperature, we will talk about today. So when the temperature gets below the degeneracy temperature, the system gets, the boson gets to be condensate and called Bose Einstein condensate. It was found by the Bose, an Indian mathematician, and Einstein, well-known scientist. They both formed this condensate and named as Bose Einstein condensate, Bose Einstein condensation. Okay, so now you understand. I've gave you the introduction about what is a Bose Einstein condensation. Okay, so let's move on toward our lecture and let's see what is Bose Einstein condensation. So let's turn on our light. Yeah, so let's see that. First we talk about, now you've seen what Bose Einstein condensate is, what basically we are going to do, what we are going to study today. So Bose Einstein condensation is Starting from the Boltzmann distribution function for the boson, we have two distribution functions. Boltzmann distribution function, we can say Bose statistics for the fermion, and for Boltzmann distribution function for the fermion, and Boltzmann distribution function for the boson. This is the Boltzmann distribution function for the boson. They have this is here is the density state, okay, state density, you can say this is, and its value is equals to, we have calculated this value for bosons, so in 3 dimension, density of states in 3 dimension, and it is equals to 2 pi over h. You can see this value is equals to this term. So let's say then, when this energy E equals to 0, when this energy E equals to 0, what happens then? This whole factor gets 0, okay? This gets 0 and it multiplies here and it makes all of these factors 0, which means that the G of 0 does not exist. G of 0 here is equals to 0, okay? Okay, wait. This G of 0, this G of 0 is equals to 0, okay? So when this G of 0 is equals to 0, which shows that the energy state does not exist. This means that there is no probability. This is the probability density. We can say the number of particles via number of bosons. This gives us this probability distribution function gives us the number of particles or the number of bosons. Okay, so when this factor gets 0, this whole factor gets out to be a 0, and we can say that we don't have any number of bosons with energy 0. Okay. But in a Bose Einstein condensation, when we say that when the temperature approaches to absolute 0 Kelvin, we obtain a matter, we can say, and which is called a quantum wave, which is called with the same quantum wave, matter with the same quantum wave, which is called Bose Einstein condensate. So let's talk about next. What we are going to do is, and we said that n is a total number of boson. N of 0, this is n of 0 is number of bosons with energy 0. So basically we can say that these are the number of bosons on ground state, okay? So, and this is any instant number of boson at any instant E, okay? Any number of arbitrary number of bosons with energy E, with any instant energy at any instant energy E. Now what we are going to do is, we named it as, when we solve this equation, if you want the complete solution for this equation and this all, go to my website, Learn Daily Physics, and I've gave you a tutorial video in my channel also. So go to my website, Learn Daily Physics, and you can download the notes for chapter number 3, and it's of page 153. Okay, so this n is equals to n naught plus n prime, and the value of n prime have been derived there. I've written as it is. So n prime is equals to v over lambda cube f of this we call epsilon. I don't know what this symbol is called. Let's call it epsilon. Okay, so let's wait. Let me see what this symbol is called. Okay, so I've searched this function, and this function is called xi. Okay, it's xi xi. Okay, so xi is equals to, and the value of this function xi is equals to exponential mu over tau. This tau is equals to kBT when energy approaches to 0, and this mu is that chemical potential. So now for the boson, Bose Einstein condensate, we have two assumptions for the Bose Einstein condensate, and it is that tau equals tau approaches to 0, and the mu approaches to minus tau over n. Okay, tau approaches to 0 and mu approaches to minus tau over n. As from equation 2, this is our equation number 2, and this is our equation number 2, and we can say that from equation 2, putting this above value here, this mu equals to, this is approaches to, so mu equals to minus tau over n. Tau will be cancelled out this with this one, and it will, the remaining part will be exponential power minus 1 over n. Now for the large value of n, let's say that the total number of bosons are very large and approaches to infinity, for example. Then xi will be equals to e minus 1 over infinity, which is equals to e power 0, 1 over infinity equals to 0, and this factor is equals to 1. So when tau equals to 0, xi equals to 1. Okay, so let's see what happens. Now we are going to do, what we are going to do is, we are going to put this value, this xi equals to 1 in this above equation. To calculate the number of boson, we will put this value. Now we have calculated this for the Bose Einstein Condensate. Tau equals to 0, xi equals to 1, and this xi will be put in here, and we are going to put its value. Let's see what happens next. So this was our equation, and we put the value of xi here 1. So now we know that this function have a constant value, and its value is equals to 2.612. Putting this value here, 2.612, it will be equals to 2.612 v over lambda cube. So this is the basic equation which gives us the number of bosons in excited state. Okay, so these are the number of boson in excited state. I've told you earlier that this is the total, this is in ground state, and this is the number of boson in excited state. So what we are going to do is, the value of lambda we have calculated when we were calculating the density state, 3-dimensional density state for the boson. We have calculated this value lambda is equal to this term here, and we know that temperature have a direct relation with energy. I've shown you that in the animation that when you increase temperature, the kinetic energy increases and the randomness increases, energy increases. When you decrease the temperature, the kinetic energy decreases, and the decrease in the kinetic energy makes the overall temperature have a direct relation with energy. We can say simply, we can say that T is directly proportional to E. Now let's see what degeneracy temperature is. To understand Bose Einstein condensation, you have to understand what degeneracy temperature is. So let's say we have a boundary here on the back side of it. We say that we have a boundary T naught. This is degeneracy temperature. Okay, at this temperature, all of our bosons are up here. Okay, and as the temperature gets, this is T. Okay, T, when T is greater than T naught, all of our bosons are here. Okay, okay, all of will be here. When T is equals to T naught, again they won't be here. But when the T is less than T naught, they will rapidly jump from this higher energy state to the lower energy state. How they will, we will see right now. But this T naught is the temperature below which the bosons are in ground state. Okay, the T naught, the degeneracy temperature, is a temperature below which all of the bosons are in, we can say most of the boson are in ground state. So n prime is equals to 2.612 v over lambda cube. We have derived this equation here. So putting the value of lambda from above, so we will form this equation like this. We named it as equation number A, and let's see that for n prime, we said that for any instant, as I told you, the temperature is T for any instant temperature T for any value. But this T naught is when we have n. Okay. For the n number of bosons, we have T naught. For the n prime number of bosons, we have T. Okay. So this is the difference between equation A and B. Dividing equation A and B, all of the factors are common, they will cancel out with each other. The remaining factor is equals to T over T naught. So dividing this equation and this equation, we will form this equation. So now you can see that n multiplies here and n prime is equals to n over T. Powers are here multiplied above and below, and n over T naught 3 by 2, and this is the equation. Now you can see that this factor here is a constant factor. This factor here is a constant factor, and from this we can say that n prime is directly proportional to T cube by 2. Okay, T power 3 by 2. This is the relation of number of bosons in excited state with temperature. Okay, this is the relation. This is how we can relate this with the temperature. Okay, number of bosons in the excited states can be related with the temperature in the case of Bose Einstein condensate. So let's talk about from equation 1. What was our equation 1? Our equation 1 was n is equals to n naught plus basic equation, this equation. From this equation, what we are going to do is we are going to calculate n naught equals to n minus n, multiplying minus here, basic steps. So now we have calculated the value of this n prime. What is the value of this n prime? Let's see that this was the value of this n prime from equation number 3. From equation number 3, I put this value here and n is taken common here. And we have in equation a basic equation for n naught. We can say that this is the equation through which we can relate degeneracy temperature. Okay, because it contains total number of bosons, ground state numbers, and everything is present here. Every necessary detail is given here. So we say that when T approaches to T naught, what does this mean? That your temperature is at degeneracy temperature. At degeneracy temperature, this factor T will be equal to T naught. They will be cancelled out and equal to 1, and 1 minus 1 will be equal to 0, which will lead us to n naught equals to 0. Okay, so n naught equals to 0. What is n naught? N naught is the number of boson in ground state. This equation tells us that when your temperature is degeneracy temperature, then what happened? This degeneracy temperature, at degeneracy temperature, you don't have any number of boson in ground state. Okay, you can say that this is the minimum temperature at which number of boson are not allowed to stay in a ground state. Below this temperature, they will be allowed. Okay, so the rapid increase in the population of broad states below of ground state below T naught. So I told you that as the temperature decreases, as T gets lesser than T naught, we have a rapid increase in the population of ground state below T naught for a Bose gas. What is a Bose gas? We have an ordinary gas and a Bose gas, which shows Bose Einstein condensation is called Bose gas, which don't are called ordinary gases. Okay, gases. So for a Bose gas is called Bose Einstein condensation. This process, that their rapid jump below T naught, all of their energy state rapidly jump to ground state. Let's have a look again on our animation. that how we've calculated our animation here. So wait a little bit. Here we have, okay, here we have, I should have turned off my lights. Okay, now you've seen that, let me pause it here, that at T equals to 0, at here, you can see that we have very low temperature. All of these are at ground state. We have some value of T naught which have negligible amount of boson. They are showing one boson which is very negligible as compared, oh, this one is other, now. So this is very small. Okay, we have one boson. We can say that we don't have any boson in the ground state at a temperature T naught. But below T naught, let's see, this is the temperature. Below this temperature, we have a rapid increase in bosons. Look, small change in the temperature gets a large rapid change in the number of boson in ground state. So this temperature is called degeneracy temperature, and this rapid change is called Bose Einstein condensation. Okay, so let's see how they rapidly change. Okay, so when T gets 0.9 of T naught, let's say that we have T equals to 100 Kelvin, T naught equals to 100 Kelvin, and putting this value of T naught, I'm just for your understanding, I'm telling you this example. So T naught is equals to 100 Kelvin, putting this value here. So T will be equals to 90 Kelvin. Okay, this means that T equals to 90 Kelvin from this equation. So T is less than T naught, which means boson will rapidly jump. T is less than T naught, boson will, there will be a rapid increase in the population below T naught. Okay, so N naught will be equals to 1/6 of N. Okay, 1/6 part of the total number of boson will be at ground state at this temperature, at 90, for example, at 0.9 of T naught. Okay, so how this, I'm solving this for 0.8. So when T is equals to, let's say, 0.8, similarly T naught equals to 100 Kelvin, and T will be equals to 80 Kelvin, which is less than T naught. So putting that value here, T naught, this is T naught also here. So T naught will be cancelled out with this T naught, and solving out, it will be nearly equal, N naught will be nearly equal to 1/3 of total N. Okay, so which is showing that the 1/3 part of, with the small change in the temperature, a large number of bosons are jumping down to the ground state. Okay, so the heat capacity for a Bose Einstein condensate is given by CV is equals to this factor, and from this is a constant factor, and we can say that CV is directly proportional to T power 3 by 2. If you have studied the Einstein theory for the latest vibration, or Einstein latest theory, so which is basically the Einstein model for the solids, Einstein model, Debye model, latest vibrations we have seen. So in the Einstein model for the solid, in solid state physics you've discussed, in statistical physics you've also discussed that. So the specific heat theory for the Einstein theory, for the Einstein solids, we can say Einstein model, the specific heat in Einstein model, the CV have a relation TQ. This is for any ordinary, it was for the ordinary solid. But now we have a Bose Einstein condensate and it have a relation T power 3 by 2. Okay, there is a difference between Einstein model and a Bose Einstein condensate, and this is the difference. Okay, next we have an example of helium. I am leaving it to you, so you can go there on my website and you can check on the book also. So 153, at page 153. So when the temperature gets, for a helium, when the temperature gets 2.19 Kelvin, what happens? We achieve helium is a gas, and helium gets an equilibrium state between two phases, two transition phases. One is a gas phase and the other one is liquid phase. So they both get at equilibrium, and they have a graph like this. Let's see that. This is the temperature and this one is CV, and this is, let's see that they are here, and this is 2.19 Kelvin. Okay, this is in Kelvin. So this is equilibrium. Okay, so they both achieve equilibrium. This is, let's say, gas. This is temperature is decreasing. This will be the liquid phase, and this is a gas phase. They both get in constant. Look, they are meeting up here and they will be constant with each other at this temperature. Okay, at this constant temperature, CV is increasing with the constant factor here. So this was the Bose Einstein condensation. So it was a lengthy topic a little bit. Understanding was quite lengthy, and so I hope you understand everything. So thank you very much for your time, and assalamu alaikum.